So let's find the domain of g of f. Now before we do that, let's take a look at what our function looks like. G of f of x is equal to g of f of x, which is equal to what? Well, we're going to take the function f this time and substitute it into our g function. So we get something that looks like this. The square root of 5 minus f, which is negative 10 over x minus 4. And we'll simplify that slightly. Okay, now I'm going to leave it like that for now. Okay? Now, let's take a look. When we're trying to find the domain of a composite function, we always start with the function on the inside. That is, we always try to find the domain of the function on the inside, which is f in this case. So let's find the domain of f. Okay? Well, the domain of f is going to be all real numbers except 4. Okay? It's a rational function. They're defined everywhere except the points in which the denominator is equal to 0. So negative infinity to 4, union with 4 to infinity. All right. So the domain of the composite must be a subset of this domain. All right. So let's turn our attention back to our composite function. Now let's simplify this a little bit. If we were to get a common denominator and add these two expressions together, we're going to get 5x minus 10 all over x minus 4. And you can go ahead and do that. All I did was I combined using a common denominator. All right. Now then, what do we know? Well, because we're dealing with a square root function, we know that whatever is under the radical must be greater than or equal to 0. So what we have to do, we have to set 5x minus 10 over x minus 4 greater than or equal to 0. Okay? And then we have to pull out any points necessary out of our original domain. All right. So let's solve the inequality 5x minus 10 over x minus 4 greater than or equal to 0. All right. Now this is a skill you should have acquired earlier in the text, so I'm going to kind of go quickly through it. All right, so here we have a rational inequality. The first thing that we like to do is find our boundary points. Those are the values of x for which the numerator is 0 and the denominator is 0. Our boundary points in this case are 2. That gets us 0 in the numerator, and 4. That gets us 0 in the denominator. We plot those 2 points on the number line. Notice that we have a solid dot at 2, because if we substitute 2 into our expression, we get something equaling 0. However, we're going to represent 4 with an open dot, because if we substitute 4 back into our expression, we get 0 in the denominator, which is never permitted. So we're going to divide our number line into 3 intervals. Okay, and let's take a test value from each interval. Well, in the first interval, I see that 0 is in interval 1. We can choose 3. That's in the second interval. And maybe we'll choose 5 out of the final interval. All right, so let's substitute our test values into our expression. Substituting a 0 into the numerator gets us a negative value, divided by another negative value when I substitute 0 into the denominator, and a negative divided by a negative gives us a positive value. Moving on to the second interval, using our test value of 3, if we substitute 3 into the numerator, we're going to get 15 minus 10, which is a positive value, divided by 3 minus 4, which is negative 1 in this case, but I don't care about what it is. I'm just worried about the sign. So a positive divided by a negative is a negative value. And finally, substituting a test value of 5 into our expression, we are going to get a positive value in the numerator and a positive value in the denominator. All right. So, what are we looking for? Okay. We want our expression, this was the expression under the radical, we want that expression to be positive. Okay. So the solution to this inequality is negative infinity to 2, including the 2, union with 4 to infinity, not including the 4. Notice that we excluded all values between 2 and 4 from the domain of f.